All right, so we're looking at section 2.7 now, and 2.7 covers polynomial and rational inequalities. And we're going to start off with polynomial inequalities. The definition of a polynomial inequality is that it's any inequality that can be put into one of the forms f of x is less than 0, f of x is greater than 0, f of x is less than or equal to 0, or f of x is greater than or equal to 0, where f is a polynomial function. Right, so for instance, here we have a polynomial function, x squared minus 7x plus 10. Let's say that's the function we're dealing with. So we're dealing with this function right here, and we can kind of look at the graph of this and visualize what greater than 0 would be and what less than 0 would be. That polynomial, remember, if we're talking about f of x is equal to this thing, that's the same thing as saying the y is equal to that thing. So if y equals this, and we're looking for where this is greater than 0, well, where is y greater than 0? It's greater than 0 above the x-axis. Where is it less than 0? If this was less than 0, then it would be less than 0 below the x-axis. So if we can solve a polynomial inequality where we're greater than 0 or less than 0, it's a little easier to visualize and see what we're talking about. But in the same way, understand that if we talk about this being less than negative 10, it's still the exact same graph. To actually get where it's going to be above and where it's going to be below, we have to solve for 0, because that's kind of the point that we're dealing with. So the x-intercepts 2 and 5 are the boundary points. Notice that it's greater than on the light blue here. Then once it hits that boundary point, or that 0, the x-intercept, all those things that we've called that thing, it's below the x-axis and less than 0. And then once it gets to 5, the other x-axis, x-intercept, whatever you want to call it, then it's going to be greater than again. So the places where it can be less than and greater than 0 are going to happen at those values right there, at those 0 values, at those x-intercept values. A 0 and x-intercept, they're all the same thing. All right, so the procedure for solving polynomial inequalities are to express the inequality in the form f of x is less than 0, f of x is greater than 0, where f is a polynomial function. All right, then you're going to imagine or think of that equation as f of x equals 0, and you're going to solve it. Those are going to be the boundary points, the real solutions only. Now, if you have imaginary solutions, then it's not something we can deal with, because what we're doing is these boundary points, locate them on a number line. They are the ones that's actually splitting the entire number line into parts. For instance, with that last example we were looking at, remember the x-intercepts were at 2 and at 5. And we found out that it was greater than 0 here, less than 0 in between 2 and 5, and greater than 0 over there. So once we find these boundary points, we're going to draw a number line, and we're going to let those boundary points be on there and determine what's what. Because remember, the boundary points are the only places where it can change value. All right, so that's this part right here. Locate those boundary points on the number line, therefore dividing the number line into intervals. Number 4, choose one representative number called a test value within each interval and evaluate f at that number. So with the one we were dealing with here, we got 2 and we got 5. If I choose an interval over here, I might want to choose 0 because it's easy to plug in. I'd have a test point of 0 between 2 and 5. We might use 3. And greater than 5, we might use 6. So we would take these values right here, we would plug them into the f of x. If those values are if that value is positive, then f of x for that entire interval is positive. Because remember, what do we know about these points? Those are the only places where the sign can change. The value has to go to 0 for you to go from a negative number to a positive number, or from a positive number to a negative number. So that's what we're looking for here. Because we set these equal to 0 and found these two values right here, those are the only places where it can change sign. All right, and the same thing, if the value of f that for our test value is negative, then all the values in that interval are going to be negative as well. All right, so then you want to write a solution set selecting the interval or intervals that satisfy the given inequality. So this procedure is also valid for less than if less than is replaced by less than or equal to, or greater than is replaced by greater than or equal to. However, if the inequality involves those, you must include the boundary points equaling 0 in the solution set. So that just means if you're doing interval notation, you're going to use brackets instead of parentheses at those values. Not at infinity though. Remember, that's never going to be a bracket. Alright, so let's solve one. Solve and graph the solution set on the number line. So we've got 2x squared plus x is greater than 15. So the very first thing we want to do is we want to get this thing greater than or equal to, or greater than 0. We're going to move that 15 to the other side. When we do, we're going to have 2x squared plus x minus 15 is greater than 0. Alright, so then we want to think of this thing as 2x squared plus x minus 15 equals 0, and we're going to solve that. So of course we're going to have to do bottoms up. So we're going to multiply here, we're going to have x squared plus x minus 30. And I'm not going to do equals 0 because technically it's not equal 0 anymore. It's a new equation. But I'm going to be able to factor this. So x squared plus x minus 30, we're going to have x and x. We're looking for different signs, so 1 plus, 1 minus. And numbers that multiply to give me 30 and subtract to give me 1. Well, that'll be 6 and 5. And because this term right here is positive, the larger number goes with a positive. And then I'm going to divide by whatever I multiplied by up here at the top. Remember, the way I got 30 was I multiplied 2 times my 15. So now I'm going to divide by 2, there and there. Here, 6 divided by 2 is going to give me 3, so that's x plus 3. Here, 5 and 2 won't divide evenly, so that means that this 2 is going to move out in front. So you end up with 2x minus 5. Alright, so now once I've done that, I can put it back to being equal to 0. So my key values, those boundary points, are when I have x plus 3 equals 0, which means x equals negative 3, and when 2x minus 5 equals 0, which is going to be x equals 5 halves. So those are my boundary points. Those are the only places where I can change from a negative to a positive or a positive to a negative. So when I draw my number line, and this is just for test points, this is not actually going to be my answer part. but I'm going to go ahead and draw a number line anyway. And my boundary points are on these hash marks, so -3 and 5/2. So you want to choose some value that is less than -3. Don't make it complicated. I'm going to choose -4. Some value between 3 and 5/2. I'm going to choose 0, easy to deal with. And then some value greater than 5/2. Well, 2 goes into 5 2.5 times, so I'm just going to go ahead and say 3. Larger than that, so I'm good. All right, and then I'm going to go back and plug these values in to my original function and see whether it's greater than 0 or not. That's what you're checking. Is it greater than 0 or not? That's all you're asking. All right, so if I plug -4 in right here, I'm going to get 16. Because -4 squared gives me 16. And I have 2 times 16 plus a -4 minus 15. Well, what is 2 times 16? That's 32. And 32 minus 4, adding a -4, is 32. Sorry, 32 minus 4 is 28, and 28 minus 15 still gives me a positive 13. So is 13 greater than 0? Because that's what I'm looking for right here. Yes, it is. I'm going to put a check mark. So that interval has to be in my solution set. Now, what happens when I plug in 0? When I plug in 0, this one's going to become 0, this one's going to become 0, and I'm asking myself literally, is -15 greater than 0? Well, -15 is not greater than 0, so that interval, I'll put an X down, that will not be part of my solution set. All right, and then let's say that I put 3 in there as my last test point. So 3 squared is going to give me 9. 2 times 9 gives me 18 plus 3 minus 15. And what does that equal? 18 plus 3 gives me 21. 21 minus 15 is going to give me 6. 6 is greater than 0. So that is part of my solution set. So our solution set, and I'm going to write it in the interval notation first. Starting over here, you got -infinity all the way up to -3. So -infinity to -3. I'm not including -3 because it's only greater than. And at -3, what's it equal to? -3 would be equal to 15. All right, and then that's going to be unioned with this part over here, which is from 5/2 all the way up to infinity. All right, so there's my answer in interval notation, but they wanted our solution on a real number line. So remember, we've got -3, and we've, like I said, we've already done it right here. This is just going to be the prettier graph, if you can really say that about any of my graphs. All right, so at -3, I'm going to start my solution, but it's an open dot because I'm not including -3, hence the parentheses, and then everything lower than that. All right, and at 5/2 going up, remember that's part of my solution set. So I've got, once again, an open dot here, and everything to the right of that. So there's my solution set on the real number line. All right, now I want you guys to try this. You work it out yourself. Pause the video, work the problem out, and then once you get it worked out, turn the video back on and I'll show you my solution and you can check your work. I'm going to show you the solution here. Guys, try it. That's how you learn. You learn by making mistakes occasionally. But you got to try it to make a mistake. So I'll show you the solution in 3, 2. All right, so here's the solution. This one was a little easier than that other one because of the factoring being a little easier. So we got x squared minus x is greater than 20. Move the 20 to the other side, you get x squared minus x minus 20 is greater than 0. Factor that, you get x plus 4 and x minus 5. Therefore, our boundary points are -4 and +5. So when we do a little bit of testing, we're going to do -5, 0, and 6. And guys, you can choose other values other than those. Those are just the ones I picked. The boundary points, however, that's part of the problem. So you should get that. These values are just values that we picked. So -5, when I plug that in, I'm going to get 25 minus a -5, which is the same as adding 5. So I get 30 minus 20, which is a +10, which is greater than 0. So that's why I put a check mark there. That interval, because of that one test point working and me doing it right, means that that's going to be a solution. Now when I plug in 0, I'm going to get 0 minus 0 minus 20, which is -20, which is not greater than 0, so it's not part of my solution. And the same thing with 6, I plug it in, I'm going to get 36 minus 6, which gives me 30, and 30 minus 20 gives me 10. Still, that 10 is greater than 0, therefore that side over there is part of my solution set as well. So there's the graph of my solution set, and the solution set here would be -infinity to -4, parentheses all around, unioned with, remember that just means that we're talking, when we do a union, we're talking about this interval and that interval, and 5 to infinity. So when we do a union, we're talking about this one and that one. Remember, there is a such thing as an intersection also, and that's an OR. All right, so check your work. Moving on. All right, so let's solve one just a little more complicated, not too bad. We've got x cubed plus x squared is less than or equal to 4x plus 4. So of course the very first thing we're going to do is we're going to move everything over to the left side. So we're going to have minus 4x minus 4. It's going to be less than or equal to 0. All right, now with this one, it's an x cubed, but remember we've got some ways we can factor cubic, and this one you're going to use by factoring by grouping. So I'm going to do my -4x over with my x cubed. X cubed minus 4x plus x squared minus 4. Oops, no x there. And that's less than or equal to 0. So now over here on this one, I have a common factor of x. I'm going to take it out. That leaves me with x squared minus 4. And over here, I'm going to take out a factor of 1. You got to take something out. So I'm going to take out a factor of 1, and I'm going to get x squared minus 4. Now, the fact that these things are both the same means I can now factor those out. So x squared minus 4 times x plus 1 is less than or equal to 0. Now, of course, this is a difference of squares. So we're going to have x plus 2, x minus 2, x plus 1, and that is less than or equal to 0. All right, so let's go ahead and set up our number line. If we set each one of these equal to 0, x plus 2 equals 0 is going to give me a value of -2. X minus 2 being equal to 0 is going to give me a value of 2. and x plus 1 being equal to 0 when I move it over would give me a value of negative 1. So we set all these up on our number line, negative 2, negative 1, and 2. So these are our boundary points. These are the points we need to make sure we get on that line. Then we're going to choose values in between them. So some value less than negative 2 is going to be negative 3. Some value in between negative 2 and negative 1. This one you're just going to have to suck it up and use a fraction. Negative 3 halves. Some value between negative 1 and 2 I can use 0. Some value greater than 2 I'm going to use 3. So now this case I have 4 different intervals that I'm checking. So when I choose each one of these and put those values in, I want to know what my value is when I plug it in. And guys, you can put in here, you can put in here. Either place, all you're testing for, does that test value give me a solution? Is it true? Does it make a true statement? If it makes a true statement, I put a check mark. If it makes a false statement, I put an X. I'm just saying, does that number that I've chosen to represent that interval, does it make a true statement or a false statement? That's the check mark or the X. So if I put in negative 3 here, I'm going to get negative 3 to the third power, which is negative 27, plus negative 3 squared, which is 9, minus 4 times negative 3, which is plus 12, and then minus 4. All right, negative 27 plus 9 is going to be negative 18. Negative 18 plus 12 is negative 6, and negative 6 minus 4 is going to be negative 10. So that is less than or equal to 0. So that's part of my solution set. Negative infinity all the way up to negative 2 is part of my solution set. Now, the good thing about this is the fact that we only have to determine, is it greater than or equal to 0 or is it not? So when we do something like negative 3 halves, we can usually look at it and see whether it's going to be positive or negative. So that's a good thing. So if we take and we cube negative 3 halves, we're going to get negative 27 over 8 plus negative 3 halves squared is going to be 9/4 minus negative 4 over, or times negative 3 halves is going to be, it's going to be 6 plus 6, and then minus 4. All right, so 8 will go into 27 3 times. 4 will go into 9 2 times, plus some. So we can get an idea of whether or not this is going to be positive or negative. So 3 plus 2, negative 3 plus 2 is going to give me a negative 1, plus 6 is going to give me positive 5, minus 4 gives me a positive 1. So it's going to be positive, which is not going to be true. So I'm looking for less than or equal to. And guys, if you got a calculator, it's usually a good idea to do that a little more close. But with this one, it's pretty easy to do. Just be careful that you're not guessing, like, you know, saying this is 3.9 and it's and trying to say that it's 3. Those, you know, when you've got huge fractions that are tacked on, huge decimals, that can throw you off pretty quick. All right, if I plug in 0, it's going to be really easy because I've got 0 plus 0 plus 0 minus 4. So negative 4 is greater than or less than or equal to 0. Yes, it is. I get a check mark. And then 3. Let's go ahead and do the 3. 3 cubed is 27. 3 squared is 9. Minus 4 times 3, which is 12. Minus 4. 27 plus 9 is 36. 36 minus 12 is 24. 24 minus 4 is going to give you 20, and 20 is not less than or equal to 0. So that's not part of my solution. All right, so just in interval notation, my solution is negative infinity to negative 2, this part, and then union with negative 1 to 2, this interval here. Now, if I wanted to draw it on the number line, which our instructions tell us to do, all we have to worry about is where it changes, which is, by the way, in this case, everywhere. So negative 2, negative 1, 2, and then what do we know? We know that greater than or equal to, I forgot that, greater than or equal to means I'm going to include these points. So that means I'm filling in the dots and shading less than, going off to positive infinity. And then in between negative 1 and 2, I have a closed interval, a little line segment there. All right, now when we deal with what's called a rational inequalities, we're dealing with rational equations that are now inequalities. In other words, the rational equations that you've been graphing, now we're talking about setting them greater than 0, less than 0, greater than or equal to 0, less than or equal to 0. So we're dealing with this part right here, something similar to that. Now, the first step in solving a rational inequality is to bring all the terms to one side, obtaining 0 on the other side. Then express the rational function on the non-zero side as a single quotient. The second step is to set the numerator and the denominator of f equal to 0. These solutions are going to serve as the boundary points. And then from there, once you get the boundary points, it's just the same. Test and see if it works. If it works, you get a check mark for that interval. If it doesn't, you get an X for that interval. So let's do one. All right, so looking at this one, we want to get this thing equal or greater than or equal to 0, so we're going to move the 2 over. So we end up with x plus 1 over x plus 3, and that's minus 2, greater than or equal to 0. Now I need a common denominator because I need to get this in as one fraction. So I'm going to multiply top and bottom, and this is top and bottom, by x plus 3. So now I have x plus 1 over x plus 3 minus 2 times x plus 3 is going to give me 2x plus 6 over x plus 3. And this is greater than or equal to 0. Alright, so now you want to combine these into one fraction. We've already got our common denominator, so we know that's going to be on the bottom, x plus 3. And then x minus 2x gives me negative x. 1 minus 6 is going to give me negative 5. All right, so now we're going to set the top and the bottom equal to 0, because when the numerator is equal to 0, that's when the actual rational function is going to be equal to 0. When the bottom is when it's equal to 0, it's going to be when it's undefined. So we want to find both of those. So negative x minus 5 equals 0, and x plus 3 equals 0. So when we solve this, we're going to move the 5 over, divide by negative 5, and we're going to get x is equal to negative 5. Move the 3 over, we're going to get x is equal to negative 3. So these are boundary points. So once again, we do our little test. We got -5 here. We got -3 here. We choose some test values. -6. -4 and 0. Alright, and then you can plug it in anywhere, but this is going to be about the best place to plug it in. And I'm going to start with a 0 because it's really easy. If you do 0, you're going to have -5 over +3, which is greater than 0. No, I don't think so. It's less than. So no, that's not going to be part of our solution. If we plug in -6, what is -6? That's a +6 minus 5, which is going to give you a plus on top. And -6 plus 3 is going to give you a minus on bottom. What's a positive divided by a negative? Well, that's going to be a negative, and that is not going to be greater than or equal to 0. So that means that with a negative, this is not going to be part of my solution either. So I choose -4. I plug in -4. So a -4 gives me 4 minus 5, which gives me a negative number. And then -4 plus 3 is also going to give me a negative number. Negative divided by a negative gives me a positive number, which is going to be greater than or equal to 0. So that means my solution set are all the numbers in between -5 and -3. Now, because of the greater than or equal to, we're going to go back and we're actually going to plug these two in just to double check. Which one's going to make this true, and is one of them going to make it true and one of them not? We just want to double check. So if I choose -5, I'm going to have -5 plus 1, which is going to be -4, and -5 plus 3, which is going to be -2. -4 divided by -2 is going to be equal to 2. So that one checks. And if you plug in -3, -3 plus 1 gives me -2, and -3 plus 3 gives me 0. So what do I know? I know that that is not going to be part of my solution set. Now, here's the thing. Why do we know it's not going to be part of our solution set? Well, because it makes this thing undefined. And if we're looking for the solution set, we're looking for all x. For the very first thing, for a solution, it has to be part of the domain of the function. The -3 is not because of the division by 0 here. So that means we do not include, we include -5, but we do not include -3. So when we write our interval, we're going to have our interval as -5, bracket, comma, -3, parentheses. The -3, because it makes this denominator equal to 0, it's not going to be part of our solution set because it's not even able to be in the graph, in the function, without causing inequality or undefined. So then, of course, when we draw our number line, we've got -5 over here, we've got -3 over here. This one would be a closed dot. This one would be an open dot, and everything in between. All right, so that's all. That's one of each one of the problems. If you've got questions, make sure you write them down, ask them when we get to class, and we'll practice some the next time we see each other.